start. Good morning to everybody. My name is Matteo Cococcioni, and this morning I will talk about two aspects that are related with systems that have localized electrons. So systems, say, with some valence electrons in the d shells that are usually not complete. And those are the magnetism. So typically these systems are magnetic, develop some finite magnetization, and also correlation. So the first part of this presentation will deal with magnetism. We'll learn basically the most basic approach to deal with magnetism within DFT theory. Then in the second part of this morning lecture, Andrea is going to talk about non-collinear spin magnetization and spin orbit coupling. So you will see how this is completed with a more sophisticated approach. And then I will talk also about a simple correction you can add to the DFT functional to bring in some effect due to correlation. So we learned yesterday evening from Nicola's talk that very often when we have electrons on localized orbitals, those electrons give rise to some magnetic moment. Okay, and that moment, of course, stems out from the spin of the electrons. Okay, this is not the only condition. Of course, we need to have less electron than space to allocate them. Okay, so we need to have an open shell. Say that this is an example relating to d electrons. So you see 5 spaces here, 5 boxes. If we had 10 electrons to allocate in there, we could only place them 2 per box. Okay, so in each box, so one of them would be up, the other one would be down. The total magnetization would be 0. That's why copper, for example, is non-magnetic. In this case, the radioactivity is iron. You have nominally at least 6 electrons. So you have different choices of how to place them on those states. So first idea is, okay, let's place them coupled, trying to fill up each boxes. So we have in each box, in each state, we have 1 up electron, 1 down. So each of these states will contribute no magnetization. And at the end, since we have an even number of electrons, we have no magnetization in this first state. In the second one, instead, we try to occupy as many states as possible. And of course, this is only one choice that could have been made. Well, actually, it turns out that this second one is the one preferred by systems. So the energy associated with the second configuration of electrons is lower than the energy associated with the first one. Okay, and this is so because, well, there are many levels at which we can understand this. Say, from a classical point of view, we take into account just Coulomb repulsion between electrons and Pauli exclusion principle that says that you cannot have more than 2 electrons on the same state. So if I have electrons aligned in spin, I have to place them in different states. Okay, that means that the electrons will be on average more far apart from each other and will repel each other less. So the energy cost associated with repulsion will be lower. So that's why this energy is lower than the first one. From a quantum mechanical point of view, this is built in, say, in the antiferromagnetic character of the many-body wave function, so that when you take the expectation value of a 2-body operator like the Coulomb repulsion, you end up with an additional term that is the exchange term that is negative in this case, in the case where you have parallel spin.
What are the other possibilities, like all 4 down, because the only degenerate state is possible?
Yeah, sure. You can. I mean, this is symmetric with respect to reversal of spin.
For these 4, all 4 can be also down separately.
Yeah.
two can be up, two can be down.
Yeah, there are many other configurations.
What
Sure.
they are energetically not favorable, you mean? That's why you have not shown them. Like all these four,
Yeah.
which is single,
Yeah.
they can be all down, so that is doubly degenerate state.
Yeah.
And then it can be one up, one down, one up, one down also.
Yeah.
Four cell.
Yeah, but
There can be three up, one down.
sure.
What about all those possibilities?
There are many. They're not probably all degenerate with each other. I mean, if you place one electron down, probably there's a finite chance that it overlaps with another one. So yes, there's a chance that they will stay on the same state and they repulse more. So exactly, this is there are many configurations possible, and actually this is the most favorable one. Also, this is not the end of the story in the sense that this gives justification to the magnetism of each atom, but then you have a system and you can have also different spin arrangement between atoms. So this is one case that we will study also later on for the other problem, where you have an anti-ferromagnetic configuration. That means that the number of spin up and spin down is the same. So total magnetization is zero, although each atom has a magnetization that is different from zero. And in this case, you see there are ferromagnetic planes with opposite magnetization close to each other. Okay, so we'll see also this afternoon how to describe the different sort of spin arrangement. Okay. So this is an example of a transition metal oxide, and you also see that the magnetization is mainly only on the metal ion, okay, while the oxygen stays non-magnetic, because the oxygen basically take up the electrons and fill up its own shells, the external shells, and so in the oxygen orbitals you always have one electron up and the other one down, so no magnetization arises from the electrons around the oxygen atom. So how well can we describe a magnetic system using DFT? Well, so we can say that if we had the exact exchange correlation functional, that would be able to provide the magnetic ground state of the system, if that was really the ground state. I mean, if that was associated with lowest energy. Now, it turns out that with approximate exchange correlation functional, the one we use always, it's more convenient to have the spin degrees of freedom explicitly treated. Okay, so in the exact energy functional, we would obtain the ground state charge density associated with the magnetic ground state without doing anything else. While in the other, if with approximate exchange correlation functional, to get a lower ground state, lower energy ground state, to arrive at the magnetic ground state, we normally have to treat the two spins, at least to treat the two spin population separately. So we better introduce spin polarized quantities, starting from the charge density that we write as the sum over the spin of the two spin contribution. Each of these spin contribution is the sum over Consham states of the square of the Consham state of that particular spin, of course. And we can also define a magnetization density, that is some Bohr magneton times the difference between the density with spin up and the density with spin down. Okay. Next, we need to express the total energy of the system as a function of the spin polarized charge density, or of the total charge density and of the magnetization density. So the kinetic energy doesn't change. The external part of the energy, of course, only depends on the total charge density. so it does not depend on the magnetization density. Okay, so it's just the interaction, the classical light interaction between the charge density of electrons and say the ions. The R3 part also doesn't change because it's the classical Coulomb repulsion between two charge densities. Okay, so the only place where we have a dependence on magnetization is the exchange correlation functional. And that makes sense because, as we said, magnetism comes from first of all from the exchange term. Okay, so it's going to be in there. So how now we have a model for the energy. Still, we want to minimize it, so we want to use the Cococcioni equations, and we're going to write two separate set of Cococcioni equations for the two spin populations, for the two spin degrees of freedom. So we do this simply taking the functional derivative of the energy functional we saw in the previous slide with respect to spin up to psi I up star and psi down up star. So we obtain these two Cococcioni equations, okay, where the symbol have the usual meaning. So, for example, the external is the functional derivative of the external potential with respect to the charge density. Same thing for the R3 potential. For the exchange correlation potential, since it depends on both charge density and magnetization, we take the derivative with respect to density and then the derivative of density with respect to wave function. That will give us Bxc. That is the same for both spins. Then we also have to take the derivative of the exchange correlation energy function with respect to the magnetization times the derivative of magnetization with respect to the wave function. But this second derivative is a change sign between the two spin population because the magnetization has the derivative of magnetization with respect to the density, polarized density, change sign with the sign of the spin. Okay, so the first case we have plus Bxc, the second case we have minus Bxc. So the two basically spins solve two different sets of Cococcioni equations. Okay, still they're not separate. Okay, they're coupled. So we need to solve them at the same time because each of these terms, say especially B exchange correlation and B exchange correlation, will depend also on the other spin population. So for example, in this equation, this Bxc and Bxc will depend on both the charge density and the magnetization that also descend from this point. So the two sets of equations are coupled. So how do we obtain the in practice, in practical implementation, the exchange correlation function in a magnetic case? Suppose that you have the exchange correlation functional for the non-polarized case. Then for the exchange case, it's simply obtained. It's linear in the polarized density. Okay, so it's obtained from say scaling arguments from the unpolarized case. So since it's diagonal, so each spin population has its own exchange, basically. So the total exchange is the sum of the two contributions from the two spins. Okay. For the correlation part, instead, what normally is done in polarized functional is obtaining them as a linear combination of the unpolarized case and the totally polarized case. Okay, where the linear combination is done with this interpolating function. It is a smooth function of basically the relation between the magnetization and the density. Okay, so basically what happens is that you set your calculation, you suggest some initial magnetization that will give you some initial value for this quantity between 0 and 1. Okay, then you have a final contribution from the total polarized correlation energy functional. Also, you have a finite exchange correlation for both spin population. You solve the Consham equation, and as usual, you obtain the density and the magnetization density. You recomputed these C of R quantities, so you have the value for the interpolating function. Just 1 second. And you can reconstruct the correlation and exchange functional for the next iteration and so forth and so on in the usual calculation. Yes?
Yeah, my question was on what is the algorithm to first, is there an iteration back and forth even in getting these functionals? You evaluate the first one, which is essentially the spin-based
exchanger.
And then the correlation is independent, or do you use something from the
What do you mean if I use something?
No, I'm trying to see, these are like two independent things you calculate and then put them into the total energy.
Yeah.
Or do you have any iterations between spin and for exchange, correlation and exchange?
No, they are added in the exchange correlation function.
Okay, so the correlation is not very different for spin, right? It's the same?
No, it's not. It's not the same because you have a linear combination of polarized and unpolarized. So those two are obtained from the homogeneous electron gas in the case of LBA with zero polarization in this case, so all spin are coupled, and total polarization, so where all the spins are aligned to each other. So linear combination between the two functions will give you, that's the approximation of course, the functional for your case where you have an intermediate magnetization.
Oh, so you are not referring to electrostatic polarization, you are talking to spin polarization.
Yeah.
Okay,
yeah.
So that's what I was trying to say.
Oh, sorry. Yeah, I'm still talking about, yeah, polarized means
spin.
all spin aligned. Sorry. Yeah, maybe it wasn't that clear. Okay, this is a brief collection of different possible cases. So the first case is a rather trivial one, that is silicon is a non-magnetic system. In non-magnetic system you have that on each state, on each Consham state or on each band, if you want, you have one spin up and one spin down. So the two spin population have the same, exactly the same density of state, as you can see here. So they're exactly specular with respect to this line. In the case of a magnetic material, like for example bulk iron, instead you have an unbalance between the two. So one spin is more populated than the other one, and you can see this from the density of state. So the spin up is in the upper part and the spin down in the lower part. And if you take the integral from the bottom of the valence band to the Fermi level, you see that the number of electrons you count in this upper part is larger than the number of electrons you have in the lower part of the density of state. Okay, you can see by eye inspection this. Of course, this you could revert the spin and obtain the other exactly equivalent situation, equivalent solution, depending on how you set the spin in your input. So you can choose to have it up or down as a majority channel. Also, notice that so you have two different contributions. One, the black line is from S states. Okay, this is the lower one, multiplied by 5 actually to see them on this scale. And the red states are the D states. You can observe also that most of this imbalance between up and down, the number of up and down electrons comes from the D states, okay? Because mostly the S states remains unpolarized. So I can anticipate that there is a difference of 0.05 electron between the two spin for the S channel. Okay, so most of the magnetization comes from localized states. That is what we were saying at the beginning, at the first slide. And this is so because the gain in energy in having a parallel spin compared to an anti-parallel spin is bigger if electrons are on localized states, okay? Because they would repel more if they had a chance to get closer to each other. What happens in anti-ferromagnetic materials, like, for example, nickel oxide? Okay, this was the example I went through quite quickly earlier. So, of course, if you plot the total density of state for each spin, you should get the same number of electrons, the same density of state for both. Okay, because the total magnetization has to be zero. This is anti-ferromagnetic, and we said the number of spin up is equal to the number of spin down. Okay. However, each of these ions are magnetic, so it's spin polarized. So observe first of all the density of state of oxygen for the two spins. So you see it is exactly the same. That means that oxygen is non-spin polarized. So no magnetization, as we were supposing at the beginning, comes from the oxygen. Okay. What about nickel? Nickel, you can have nickel up on one of these planes and nickel down. So nickel up will have more up electrons than down electrons, so have a net magnetization pointing in one direction. The other family of nickel atoms will have the opposite magnetization. So we'll have exactly the same density of state, but reversed. Okay. So what was the spin up for nickel up is now spin down for nickel down. So what was the majority spin contains always the same number of electrons as well as the minority one, but the sign of magnetization has changed between the two. So they have an exactly specular density of state between the two spin channels. Okay, so that makes the sum of the three contribution over the unit cell exactly equal between the two spin states. Okay.
So where to find the level in what field?
So in this case, I use so there is a gap. So this is an insulator. So there's a gap, and the top of the valence band is around here. Okay. So you should count from the bottom of the valence band up to here to see how many electrons you have. Okay. Any questions so far? Because this is the last slide of the first part of the presentation on magnetism. This is a first initial simple approach to deal with magnetic system. You will see in the second lecture of this morning how to generalize this, how to treat spin and orbit degrees of freedom all together, solving not a Schrödinger-like equation but a Dirac equation, and how spin orbit comes into play basically in this equation. Okay. So if there's not any other question, your question?
So above the Fermi level, this high density
is a peak here. So this is the empty. This is the empty. Some of the empty d states of nickel. So nickel has 8 electrons on the d states. Okay. So you will fill up one spin completely, 5 electrons. Then you have 3 more to allocate on the down channel. Okay. And that if there's a gap, it means that these states are not equivalent to each other anymore, so they will split typically in 3 and 2, and you occupy the 3. And the 2 that remains unoccupied are pushed above the gap. So they are the conduction states here. Okay. Okay, let's. This is a summary of problems still inherent with this simple approximation that we have seen so far. So, as you have noticed, probably there's only the z component of spin taken into account. Okay, the spin is described this way. You either have a spin up or spin down. Okay, this is a simplistic description of spin. In fact, you should involve what they call the spin, the Fermi spin matrices that give you the spin in every direction. There's no specific orientation of spin with respect to say the lattice, and so there's no energy difference if you cannot actually specify a different direction than z or a generic direction. If you do this kind of calculations, you will learn later on how this instead is sometimes important when you have spin orbit interaction. And again, you will see also you will deal with the spin orbit interaction. Also, keep in mind that with this simple approximation, you have basically always states that at most are eigenstate of mz, so the z component of the spin. This is also an approximation because you won't have eigenstate of total spin. You have the phenomenon of so-called spin contamination. Okay, this is something that affects the ground state wave function of the approximate DFT functional. On the other hand, I mean, keep in mind that DFT is only meant to give you the ground state charge density. So the wave function itself doesn't have straight physical meaning. Okay.
Yeah.
Well, I just have a question. I'm confused about how do you, in the calculation, how do you select the ferromagnetism? From the beginning, you impose a magnetism.
How do I select it?
Yes. From the beginning, you impose some ferromagnetism or some anti-ferromagnetism.
So we'll see this afternoon. Yeah, exactly. I mean, when you start the calculation, so say for example, if you have a compound like this and you don't know, basically to start with whether it's anti-ferromagnetic or ferromagnetic, or if it's anti-ferromagnetic, this is going to be the lowest energy configuration. Nobody will tell you from the beginning. So basically what you do, you try and you compare the total energies. And when you set up the calculation, you have the freedom to choose the spin configuration, provided that, of course, you construct a unit cell big enough that allows you to do that. Okay, so we'll see this afternoon. And usually what you get is that if the material is as a magnetic ground state, either ferromagnetic or anti-ferromagnetic, normally can be stable in more than one spin configuration. Okay, so in this case, for example, you could obtain also a ferromagnetic ground state. Okay, that would be stable if you suggest the system to get ferromagnetic configuration, but the energy would be higher than this anti-ferromagnetic one. In the case of a system like silicon, instead, there's no usual way to get a magnetic system. We'll see this. So even if you start from a magnetic situation, a magnetic state, it would go non-magnetic.
And so this is very connected to the fact that the orbitals we consider are d orbitals?
In some sense, yes. So it's related to the second part of the presentation, in a sense, because whether or not the material will pick up some magnetization depends on the balance between two different kind of terms of the energy. So in this case, basically silicon constructs basically bands, so that are bonding and anti-bonding bonds in between atoms, okay, and prefer to fill the bonds with one up and one down spin, okay, rather than keeping the spin parallel and not making the bonds. Okay, so that's why you get no magnetic solutions, because the valence, there's a gap in between valence and conduction state, and the valence states are all filled. Okay.
And where is hidden the U parameter in that case?
I'm sorry?
Does the U interaction parameter play a role here? The Coulomb interaction still has any role, or is included very...
In silicon?
I mean, like, the U parameter of the Coulomb interaction between electrons, is it included non-explicitly here, or just...
Not explicitly, but if you include them, or in some more sophisticated functional, you still obtain the non-magnetic solution as the ground state.
Because you speak about balance between localization and delocalization. Balance is not fixed by the U parameter against the band bandwidth, for example.
So let me go on, and then maybe you will come back to this. So exactly with this, I will start the second part of the presentation that deals with a problem intrinsic to DFT, that is the treatment of correlated system. So this is exactly an example, say nickel oxide or iron oxide, are example of so-called strongly correlated system, where you have very localized d electrons that mostly stay around the metal ion. Okay, so very localized, almost atomic-like orbitals. So they, as I said, they have this rock salt structure, but the magnetization that is with these parallel ferromagnetic planes with alternate spin from the neighbors impose a rhomboidal symmetry. Okay, and sometimes this results also in some rhomboidal distortion of the unit cell. How well does DFT describe this? Well, not too well. In the case of nickel oxide, say for example with GGA calculation, GGA functional, you obtain something like this. So as I said, nickel has 8 electrons on the d state. So you see here the scheme for the d states of nickel, and they get splitted because of the crystal field of the material in say 3 groups of 3 and 2. Well, it's not exactly like this because it's rhomboidal symmetry, not cubic, but first approximation, this is what happens. And so you place the 5d electrons on say the majority spin channel, then you have 3 more on the minority spin channel, and a gap opens in here because of the difference between the crystal field splitting and the exchange splitting. Okay, and you can see this on the band structure of the material. So there is a finite gap appearing in the band structure. However, this band gap is smaller than experiments, than revealed by experiments, although you shouldn't be comparing, to be honest. And also, oxygen should be on top of the valence band rather than on the bottom of it. So there is something not coming right out of straight GGA calculation applied to this material.
This calculation is done with plane wave basis or
Sure.
algorithm?
No, plane waves with our code. The PWS. For iron oxide, the troubles are even more serious because you cannot even get the insulating state. I mean, all these are so-called Mott insulators, so they're not metal, while you get a metal with a Fermi level cut in some D manifold. So the problem is that the extra electron in the minority spin state sits right at this triply degenerate manifold here. So in a band picture, you have one electron that on an almost empty band, basically. So you get a method in the band language. So what is the problem? So the problem is that these are not like silicon insulator in some sense. So the insulating character here comes from the fact that there is strong electron-electron repulsion. So, and having this strong electron-electron repulsion prevents the electron from going around, because they would have to interact. They would be repelled by other electron localized on these states, on the other atoms. So we can, I mean, there are many ways to describe this situation. You can start from the wave function and say that there are ionic terms that still count too much, or you can start from the functional and say there is some feature of the exact DFT functional that are not well reproduced in the approximate DFT functional, and that's why you don't get a good description for multi-insulator. I think that particularly transparent, on the physical point of view, way of saying this can be, I don't know if you can see the reference here, can be obtained from this paper by Mott and Austin from 1970. Basically, you have two different quantities to compare. One is the repulsion that the electrons feel when they are at short distance from each other, say on the same site, and this is usually named U. And the other one is the so-called bandwidth. Okay, so the energy gain coming from say delocalization. This is one body energy term. So this is the one that's minimized when silicon creates and does basically bonds, okay, and the bonding state are split from the anti-bonding state. And this is the energy that's minimized doing this. So you have two different extreme regimes. The first one where exactly the bandwidth, okay, is much larger than the repulsion between electrons. In that case, the energy is minimized by minimizing the bandwidth. This is the case of silicon, okay? And this usually happens through delocalization of electrons, okay? In the other case, where you have that the repulsion is dominant, so we are in the second case, basically the electrons don't have enough kinetic energy, let's say, although it's not all kinetic, to overcome the repulsion that they feel from other electrons localized on other atoms. Okay, so the only thing they can do is stay on their own atom, because it costs too much energy to explore other the regions around other atoms. So this is called the Mott localization. And approximate DFT functionals are not able to capture this kind of physics because U is not well accounted for. It's not well described in standard approximation to the exact DFT energy functional. Basically, it's easy to understand why, because all these approximate functional are constructed using the charge density. Okay, while in this case, when we are in this regime, you need to resolve a single electron, so the motion of electrons becomes correlated. So, and it's difficult to build in all these constraints and specific characteristic into the wave function using just, or in the potential using just charge density. Also, there is a problem that the exchange part doesn't exactly cancel the self-interaction. So there are self-interaction problems affecting DFT functional, and those also contribute to the over-delocalization of the electrons. So electrons are also more delocalized than they should be because of self-interaction. You have a question?
Yeah, just a small question. What do you mean by delocalization? If it is split across the orbital
Yeah, when the state is not localized, basically spread.
Even in the D states, for example.
Yeah. How much? The D states are normally localized.
Okay. So it has to extend beyond the D states for you to call it D localized.
Yeah, that's creating bonds or metallic bands. So when you see dispersion on the band structure, that is the signature of some delocalization. If you see flat bands, that means that those are still almost atomic-like states.
Could you explain why you is not very computing the function?
Well, because normally nobody knows. We are using approximate DFT functional, approximate functional to the real exchange correlation, to the exact exchange correlation of DFT, and we build this approximation usually using the charge density. So we use some sort of mean field approach to the problem. Okay, so one electron is interacting with other electrons that are seen like a sea of electrons, a charge density of electrons. But now if you want to describe the interaction between one electron and another one localized, it's difficult using this description based on charge density, using a functional based on just charge density.
See, in the original Hubbard model, this N term was the U term on the top of the tight binding.
Yeah.
But why they were forced to incorporate this W afterward? What was the reason to incorporate W?
So you don't incorporate W. W is this term here. This is the Hubbard model. Okay.
So this without U, this is basically tight binding. First part is basically tight binding. Now this W is within T, you mean?
Yeah, W is the single particle term of the energy. Okay, so it's actually the Fourier proportion to the Fourier transform of T. It describes the open term between neighbor side states. Okay, so it's basically the kinetic plus the interaction with ions. It's one body term of the total energy of your system. So exactly, the idea is this sort of problem is usually handled within model Hamiltonian, and the most used one is one of the most used one is the Hubbard model here, that has exactly an open term. So this operator will annihilate one electron on J side and recreate it to the I side. So describes an hopping process of the electron, and also contains the interaction between electrons when they're located on the same atomic side. So these are the number of electrons on I will spin up and the other one will spin down. Okay. So this model contains the two features we were discussing about in the previous slide, because they are the U, the interaction, and the T, that is proportional to the Fourier transform of W. So the idea is to correct the DFT functional based on this model. Okay. So we want to incorporate somehow the physics of this that comes from this model into the DFT energy function.
HC stands for Hawking conjugate?
Oh, this is emission conjugate of this other term.
H stands for Hawking.
For emission. Emission.
Emission.
So the problem is that, well, it's not a problem, that the first part is usually quite well described in DFT, so we only want a correction that improves the description of the second part. Okay. And this is DFT plus U is a simple way to do this. Okay, so one of the simplest actually. and it consists in a correction to the energy functional that is modeled on the Hubbard Hamiltonian. Okay, so you take the DFT energy functional, you add this term, and it's supposed to be modeled on the Hubbard Hamiltonian, and then you take out something that is the mean field approximation of this, that is, say, what is already contained in DFT in terms of correlation. Otherwise, you count it twice, and you don't want that. Formally, this corrective term is constructed like an R3-4 kind of functional with effective interaction. This is the way that they're normally given or described in the, and this is a fully rotational invariant formulation in the sense that if you rotate if you mix the atomic orbitals on the same side, the expression doesn't change because these will change accordingly. And the double counting is the mean field of this, as I said, so it is something like this. So the balance in between these two will give you the total correction. Of course, in the plane wave code, how do we get these numbers here? Well, it will be through projection. Okay, so we will project the Consham states onto atomic orbitals. So we have atomic orbitals that we get from the pseudopotentials. Okay, we construct block function on them, and we're able to easily compute this projection of Consham state onto atomic orbitals. This is the same thing that you do when you compute a projected density of states. Okay, you project on orthogonalized atomic orbitals, and so you compute these objects. So if you sum over all the Consham state, you get some occupation matrix of the two atomic orbitals that you are considering. Okay. So these are the ingredients that we use in our implementation. We also normally use a simpler functional, to be honest, where we neglect the effect of this parameter j, this exchange. So we end up with this corrective functional. Okay. And there's this shape n times 1 minus n, where this n is a matrix. Okay, it's the matrix of occupation on each side. So the final formula that you have is something like this, where you have the DFT energy functional plus this correction that is proportional to u, a trace of n times 1 minus n. This is the implemented one.
Yeah, so, but I'm uncomfortable with this thing that when you incorporate u, number one, how you afford to ignore j is good, because j for ferromagnetic system plays the most crucial role. Is it a nice thing to ignore?
So let me say that when we first implemented these, we tried both fashions, with j and without it, and on several material they would give almost no difference. So that's why we went for the simpler one. Now, in some material, they've recently found that considering the whole, the entire functional is, this entire formulation is more apt to fit or give better results than the simpler one. But I think it's been found for some iron nuclides, so those last materials that were discovered last year. So I think we're trying to re-implement the whole thing. But generally, it's not that you kill magnetization if you don't include J. The magnetization will come out in any case, okay, because it's already built in the DFT functional. In fact, the simpler one is also diagonal in spin, so you correct them separately. Okay.
The other point is in the previous one, when you incorporate U and you look at the projected Consham states, mathematically that's fine, but pictorially if one wants to really visualize what you basically does it shrinks the orbitals or it elongates it? Pictorially, I'm telling. Mathematically, it's fine, all these projected states and so on. But if you look at really the effect on orbital, how it really does it get more shrink towards and make the electron density a little inhomogeneous, or it pushes so that it becomes homogeneous over the spatial separation? That's one really.
So, we should separate two things. The bases stay the same. Okay, you have atomic orbitals and they stay whatever. I mean, they are what they are through the whole calculation. So, what you're going to change is the projection of quantum orbitals on each of them. Normally, what we'll see in the next slide, what happens is that you change the amount of the contribution of each atomic orbital to the quantum state. Say that, for example, you had a molecular orbital that is not very convenient for this kind of functional. So probably then what you get at the end is a quantum state that resembles more the atomic state rather than a molecular state. So you lose some hybridization, for example, with the neighbors. There is the other things. So how does it work? Why does this work? At a certain extent, of course. So this is the functional that we can use. We can write in a diagonal representation because it's rotationally invariant. And you can see as the shape of lambda times 1 minus lambda, where lambda is the eigenvalue of the occupation matrix. Okay. So if we take the potential from, or we study the action of the potential on the wave function, we have we do this by taking the functional derivative of the corrective function with respect to psi star. We get something like this. So 1 minus 2 lambda times the projection on the atomic state. Okay, so you get that if the occupation exceeds 1/2, okay, if the state is more than half occupied, then this term is attractive. So the occupation tries to grow even bigger. Okay. On the other hand, if it's less than half occupied, the system, the functional pushes it until it gets empty. So it separates empty and filled state, and the energy separation is roughly proportional to U. So that's how you get a gap in between unoccupied and occupied state, and that gap turns out to be approximately of the size of U. Okay. So let's see what the effect is in practice, and let's go back to the problematic example we had at the beginning. So this is nickel oxide. Remember that the gap was too small, and also we wanted oxygen to be on top of the valence band. And we get both of these out of the GGA plus U calculation, so you get a gap that is larger in better agreement with the experiment, and also oxygen staying on the top of the valence band.
How large did you?
It is, I believe, 4.6 eV.
0.6?
4.6.
4.6.
What is the Fermi energy for nickel oxide? About?
It has a gap, so it doesn't have a Fermi energy.
No, before you switch on the U.
Before you switch on the U, it also has a gap in the case of nickel oxide. And in the case of iron oxide, we managed to open a gap in a system where we didn't have a gap. Okay, so we had obtained a metal that is wrong, and we now have an insulator with a gap between valence and conduction state. That is about the right order of magnitude too. So with the proper U, you can open at least, you can obtain this feature at least in the tensile state of your system. Now the problem is that Okay, the functional works in some way to correct all these defects that we have, flaws that we have in the functional, but its effect, of course, depends on how big this U number is. Okay, and also, I mean, these are it's a sample of questions that people normally ask. What does this parameter usually mean? How portable is it from one system to the other one? Say that you have two iron compounds. Am I justified in using the same U for both just because I have iron on both? Or can I use the U in literature that I found on another paper to do my calculation even on the same system, although they were using another implementation, maybe another functional, they were using localized states instead of plane waves, and so forth and so on. So we better come up with an idea to compute U once forever and to use that value in our calculation. And this is what I'm going to explain. So our way to estimate this parameter. So first of all, what does U mean? So if you have an atomic system that is able to exchange electron with some reservoir, say a metallic surface, then the physical dependence of total energy on the occupation of the atomic orbital of that atom is a piecewise linear behavior, and you can see this in paper by Perdue and Levy from the early 80s, where this effect is explained. However, if you do the calculation with, say, approximate DFT and the A of GGA, you're gonna get different behavior that here is modeled like an analytic function, a parabola in this case. Okay. So you're gonna miss these discontinuities of the first derivative when the occupation is integer, and are actually connected to very important physical quantities like the difference between ionization potential and electron affinity. Okay. So suppose now that we want to correct the red curve and bring it back to the red one. Okay. So the correction looks like this function here on the bottom of the graph, and if you model this black curve like a parabola, this turns out to have the expression n times 1 minus n, which is exactly what we had in our corrective functional. So in this case, U is nothing but the curvature of the black line. Okay, this unphysical curvature that we want to eliminate is exactly this value. Okay, so this gives you an idea on how to compute the U, and in fact we want to obtain it as a second derivative of the energy with respect to this on-site occupation that we get from the projection of quantum state on atomic orbitals. Now, this is not the whole story, because say if you have an independent electron system and you start playing with potential, you can change the occupation numbers, and you get a finite contribution to the second derivative of the energy in that case. Of course, in that case, that second derivative would come from say rehybridization, so redistribution of electrons on atomic orbitals. But it's not an effect due to the electron-electron interaction. That is what we're interested in. Okay, so we need to take out that contribution coming from